Right, we are discussing cylindrical gravitational waves now. These are the waves which are usually called Einstein-Rosen waves, although they have been found by Beck already 10 years earlier, more than 10 years earlier. So we reduced, actually in the original version of the metric, we had a function which I called W of t and rho. And then we demonstrated that for a particular case, which I called case A, the W could be chosen equal to rho. And I have to write again the metric in this form, where the W, oops, that's supposed to be a mu. Where the W is equal to rho, then the metric takes the following form. So there are coordinates rho, phi, z, and t. So these are cylindrical polars. And the time coordinate, t. Rho squared, d phi squared. Here we had originally the w squared, but it's now reduced to a rho squared. So that's the form of the metric. And the vacuum field equation, which was originally a tensor equation with 5 non-trivial components, now reduces to 3 non-trivial components. I'm afraid I have to write them again because I will need them in the following. So in the original, I had equations which I denoted B1 to B5. B1 is now identically satisfied. It's 0 equals 0. B2 is, oops, second time derivative of psi minus 1 over c. Oh, that's a rho, sorry. dt squared of psi plus 1 over rho. d rho psi is 0. That's B2 prime. And then two equations which involve gamma. This is minus 1 over rho d rho gamma plus 1 over c squared dt squared psi. That's the first derivative squared plus d rho psi. 0, this is B3 prime, and then I write B5 prime. B5 prime is minus 1 over rho dt gamma plus 2 d rho psi dt psi is equal to 0. And B4, as you can check, is a consequence of these three equations. So I don't have to write it again. Yeah, if you differentiate these two equations and use the first one, then you get B4. So that's the set of equations we have to solve. And you see the nice thing is that the first equation involves only psi. So the way in which you solve this system of equations is you first deal with this equation, you determine psi, and then with the help of these two equations you determine gamma. So B2 prime is just the wave equation in cylindrical polars, a standard wave equation, ordinary cylindrical polar coordinates. And the solution is well known. If it's split off a time factor, cosine omega t or sine omega t, then what you are left with is just the Bessel differential equation for the function psi of rho. Has a general solution. Psi of t and r is a, and now comes the product of the Bessel functions and the time factor. So I think I denoted this, oops. Yes, I use the real representation. Of course, you can also write it in terms of exponentials. but I wrote it in this way, rho times omega. Omega is a real frequency, cosine omega t plus b y naught rho omega sine omega t. And j naught and y naught are the Bessel functions of order 0. Yeah, you would get the Bessel functions have an index, which is usually called the order of the Bessel differential equation. And here we only deal with the one with the index 0. The other ones show up if you have a phi dependence. Yeah? So the Laplace operator in spherical polars also involves derivatives with respect to phi, of course. But here we have a function which is independent of phi, depends only on t and rho. And that's the reason why we have only the j naught and the y naught. And then I said that if you don't want to have a singularity on the axis, then you would have to set b equal to 0. Because the y naught, the Bessel functions of the second kind, they diverge on the axis at rho equals 0. They have a finite value at rho equals 0, but the y naughts diverge. So if you want to have a solution which has no divergence in the entire 3 space, then you would set b equal to 0. But, well, actually you might say, I don't care if there is a singularity. What we are solving is a vacuum field equation. So the vacuum field equation, of course, is valid only outside of the sources. So if you have something with cylindrical symmetry, you would think that there's something like a cylindrical source, an oscillating cylinder or something like that. And then the solution would be valid only outside of the cylinder, of course. So you wouldn't care about a singularity on the axis because the solution is not valid on the axis anyway. So maybe there's some reason also to retain this second term.
Going to be an endless cylinder, or how is it?
It is infinite, yes. We have really cylindrical symmetry. Yeah. So the z coordinate goes from minus infinity to plus infinity, and the metric coefficients are independent of that. Independent of that and of phi. So it's of course it's a little bit over idealized. In the last section we had plane waves, where also the wave fronts extended to infinity. Yeah, there were planes which extend to infinity. Now we have cylinders which extend to infinity. So both solutions are a little bit over idealized, but nonetheless, one often deals with solutions of this kind, also in electrodynamics. Yeah? You also deal with plane waves and with cylindrical waves. So they are not completely unphysical, let me put it this way. Okay, so omega is any real number, and of course you can form superpositions of such solutions, because again, we end up with a linear differential equation. Yeah? In general, Einstein's field equation is a nonlinear set of equations, but in this case, for psi, we get a linear equation. But actually, the metric is not linear in psi, so this doesn't mean that the metric is a superposition of solutions, a linear superposition. But what we have to solve, this differential equation, is a linear differential equation. So we can form superpositions of solutions, if you like to do so, with different omegas, with any different real omega. We want to have oscillating solutions. That's the reason why we consider only real omegas. Okay, so now we have solved the psi equation, and then these two equations determine the gamma, right? P3 prime and P4 prime then determine gamma, if we know psi. Let me solve these equations for the derivative. They involve only first derivatives. Yeah, in general, Einstein's field equation is a second-order differential equation for the metric coefficients, but some metric coefficients only appear in first-order form, and that's the case for the gamma here. So I have the rho gamma is I have to multiply everything with rho, so then I get rho over c squared dt psi squared plus rho d rho psi squared, and I get dt gamma from the other equation. Dt gamma, again I have to multiply with rho. This is 2 rho d rho psi dt psi. Yeah? So these expressions on the right-hand side can now be calculated. And then this gives us the rho derivative of gamma and the t derivative of gamma. Of course, if I know these two derivatives, then I know gamma up to a constant. Yeah? Gamma depends on t end and of rho. If the derivatives are known, then the only freedom is in the choice of a constant. Well, and the constant of gamma, well, it could be killed by a rescaling of the rho and the t coordinate, if we want to do this. Or we could shift it into psi. That's also a possibility. So a constant is irrelevant. But the question is, are the two equations compatible? That's a non-trivial question. Yeah. So again, we have a non-trivial integrability condition. So gamma is unique up to a constant. And the integrability condition, I claim, and I prove it in a minute, the integrability condition is indeed satisfied. So this is uniqueness, and this is about existence of a gamma. Integrability condition is satisfied. Okay, let's do this. So what do I have to do? If this really is a rho derivative of some function gamma, and this is a t derivative of the same function gamma, then the rho derivative of this expression must be the t derivative of this expression. Yeah? Because the integrability condition is, of course, dt d rho gamma must be the same as d rho dt gamma. So let's do this. Let's calculate so that's what I want to know. That's the integrability condition. So I have to differentiate the first expression with respect to t. Then I get rho over c squared. If I differentiate this with respect to t, I get 2 dt psi second derivative. And here plus rho 2d rho psi d td rho psi. That's the left-hand side. And on the right-hand side, I have the rho derivative of this expression. Is this the same as 2? If I differentiate with respect to this term, then I get d rho psi dt psi plus 2 rho d rho psi d rho dt psi plus dt psi second derivative of psi. Okay, let's see. I have a 2 everywhere. What else can I do? dt, the mixed derivatives here. dt d rho, I should have twice. Let me see, is that true? Rho. Did I forget a rho here? Let me see. I differentiated this with respect to t. I think I forgot this rho here. When I differentiated this with respect to t, here was also a rho. So then these two terms cancel, right? These two terms cancel. And then I have what? Then I can write everything on one side with a dt psi times rho, say. What else do I get? Then I get 1 over c squared t psi, and I take this to the other side. Then I get minus 1 over rho d rho psi. This is this term. And this term gives minus second derivative. Minus second derivative. So is this true or is this not true? Well, let's look at the left-hand side. This here is, if I made everything correct, this should just be, equals 0 by b2 prime. Let me see, is this true? C squared theta minus, yes, I have just everything with a minus sign. So I have just everything on the other side. But that was the equation we have solved already. Yeah, we have solved this equation. We have determined psi such that it satisfies this equation. So this is true. So the integrability condition is satisfied, and this means the system of equations is solved in this way. So, well, it's a little bit involved to write down the gamma explicitly. It can be written as an integral, actually. Yeah, you can write gamma as an integral in the rho t plane. So you just write it as an integral over these known solutions. Yeah, the derivatives of psi can be calculated, and then you get the rho as an integral over these expressions. That's what in the old literature is called gamma is determined up to quadratures. Yeah, that's what is meant by this traditional wording. So yeah, we have solved our system of equations. So you see, you can choose an arbitrary real frequency with which the whole thing oscillates, and then you get a superposition of two classes of solutions. One diverges at the axis, the other one is regular at the axis. And the metric coefficients are determined in the way I've explained it. So the geometry is clear. Maybe I should have written this here in a different form. This can, of course, also be written in the form d rho plus CDT times d rho minus CDT, right? That's the same. Symmetrized tensor product here, so that the mixed terms drop out. And then you see that rho plus CT and rho minus CT are like coordinates. Yeah. So this is a type of double null coordinates again. Rho plus CT and rho minus CT are null coordinates. So the surfaces rho plus CT equal constants and rho minus CT equal constants are like hypersurfaces. And in this case, of course, they describe not plane waves, they describe cylindrical waves. Yeah? With one sign, it's an ingoing cylindrical wave. With the other sign, it's an outgoing cylindrical wave. And the whole thing is a superposition of the two waves. So if you take the regular solution, if you set b equal to 0, then you have a coordinate singularity, of course, on the axis, but it's only a coordinate singularity in this case. If you take this solution, then you have a true singularity on the axis, really a divergence on the axis. But okay, let's consider this solution with b equals 0. Then let it extend over the entire 3 space. Then you have a cylindrical wave which comes in at the speed of light. Yeah, so we have wave surfaces which move at the speed of light, meet the axis, go through the axis, perfectly regular, and then re-expand. So that this is the kind of waves which is described by this Einstein-Rosen or Beck-Einstein-Rosen solution. And everything oscillates with a constant frequency omega, constant real frequency omega. Okay, this solution, as I mentioned several times, was found by Guido Beck in 1926, I think, 25 or 26. And then about 10 or 11 years later by Einstein and Rosen again, in this paper which is lost, which was rejected in the first version by Physical Review, and the manuscript is lost. But we know from the correspondence what was in this paper, and what was in this paper was the statement that also this solution has a coordinate singularity on the axis. That because of this reason, this solution is unphysical and gravitational waves do not exist. And why did Einstein and Rosen consider this solution as singular? Because they didn't realize that what they were dealing with were actually a system with cylindrical symmetry. With Beck, it was clear from the ansatz. But Einstein and Rosen apparently tried to construct in this form plane gravitational waves. And then they had at a particular plane, so that's in our coordinates, it's rho equals 0. Yeah? At rho equals 0, which is the axis if you have cylindrical symmetry, but it's just one of the planes if you consider the phi coordinate not as periodic but as non-periodic. And then Einstein and Rosen apparently said, hey, wait a minute, I have a singularity on one of these planes, but why should the solution become singular on one of these planes? So this is unphysical, and we have to discard these solutions. And apparently, at least gravitational waves with of this type do not exist. This apparently was their solution, their conclusion. But as I said several times, this conclusion is of course completely false. What we have here is just an ordinary coordinate singularity on the axis, as it always occurs with cylindrical symmetry. You always have coordinate singularity on the axis, so there's nothing bad in this sense with this solution. And if you think of an oscillating cylinder and the solution being true only outside of this cylinder, then of course you never come close to this region where the singularity occurs, this coordinate singularity. So you don't have to care about it anyway. So yeah, these solutions do of course not demonstrate that gravitational waves do not exist, but they represent a type of idealized but nonetheless a reasonable cylindrical wave solutions. So much for the case A. So if we say Einstein-Rosen waves or back Einstein-Rosen waves, we usually mean this. So this was a case where the gradient of this function, which I call W, was space-like. And then you can consider the case that it is time-like. I will not do this in detail. I will just make a few remarks on this. So this would be the case as d rho W squared minus dt W squared with a 1 over c squared in front of it is equal to 0. So that the gradient is light-like, but the gradient should not be the 0 vector. So d rho W, dt W should not be both equal to 0. Yeah? So the gradient is not the 0 vector, but it is a light-like vector. That's what this expresses. And actually, Rosen has dealt with this case in a follow-up paper. Rosen left Princeton in 1937, then moved to the Soviet Union, where he spent a couple of years. And in this time, he wrote this follow-up paper where he investigated this case. And what came out was that these solutions are isometric to the Brinkmann solutions. Yeah? So they are not the same, actually, as a Brinkmann solution if you interpret the phi as a periodic coordinate. Yeah? So but locally, if you just consider a neighborhood of some point, then it's isometric to the Brinkmann solutions. So the cylindrical fronts propagate in exactly the same way as the plane waves in the case of the Brinkmann solution. So the solution is, I've typed it out in some detail in the notes, but I will not do this on the board. It turns out that the solution is isometric to the Brinkmann solutions, or the PP waves, as they are also called. Locally. Yeah. So you always have this problem with Einstein's field equation. If you write down a metric, this doesn't fix the geometry globally. You also have to say, what's the range of the coordinate, and are they periodic or are they not periodic? And here we have assumed that the phi coordinate is a periodic coordinate. So phi plus 2 pi is the same as phi. And if this is true, then these solutions are, of course, not globally the same as the Brinkmann solutions, but they are locally the same. And of course, there are two cases left. There's a case left that the gradient is time-like, and there's a case left that it changes its causal character from time to time. And these other cases, actually, they have also been discussed, but not in so much detail as these two cases. Other cases, the only physically relevant case is a case that the causal character changes, and this occurs when you have colliding gravitational waves are relevant for colliding cylindrical gravitational waves. Okay, so this was a brief overview on these cylindrical wave solutions. Now we have two cases. Both of them are idealized in a sense. The first case was that we have these plane waves. So you might say this is a reasonably good approximation if you are very far away from the sources. Yeah, that then the wave fronts become planes. This is not a bad idealization. Whereas these cylinders, they are infinitely long, as we have just emphasized again. Of course, they are also somewhat over-idealized. What you actually want to deal with, what you would like to have, is a bounded source, a source within a sphere, as we have considered in the linearized theory. And then the wave fronts would be, yeah, they would be topologically, they would be spheres. Of course, not metrically perfect spheres. Yeah, in the case of perfect spherical symmetry, we have Schwarzschild, and this is not a radiating solution. But we would expect the wavefronts to have the topology of spheres. Maybe in this direction, the propagation is a little bit different than from the other direction, so it's not perfectly spherically symmetric, but nonetheless, the wavefronts are more or less spheres. And the question is, do solutions of this kind exist? And they are much, much more complicated than these two classes, but they do exist. And they have been invented or discovered, as you like, just depending on how you would like to call it, by Ivor Robinson and Andrzej Trautmann. And in the remaining time, I want to say a few words about these solutions. I won't have time enough to go into full detail, because this is actually, of the three classes, it's by far the most complicated. So I cannot do all the details in the remaining time. First of all, I have to find the right page. 21. Here we are. So that's section 7.3 now. Oops. Or are there questions to the plane and to the cylindrical case?
Do we have any idea of what the source could be?
For the cylindrical waves?
Yeah.
Oscillating cylinders, yeah. Infinitely long oscillating cylinders.
And in which way should they oscillate?
I'm sorry?
In which way should they oscillate?
Periodic with time. So the radius could change. Because I have translational symmetry in the z direction, it's not possible that the density changes. Yeah. So the only change could be in the radial direction. Okay, Robinson Trautmann. So I will try to give you an idea how these solutions are constructed without going through it in detail. With double N or no, with one N? So Ivor Robinson was a British mathematical physicist who was really one of the pioneers of the theory of gravitational waves. Apart from these very few early papers, the theory of gravitational waves started essentially in the 1950s. So in the 1950s, people really looked into this in detail, and Robinson was one of the leading figures in this game. By the way, he was a very funny person. I knew him quite well. He was in Dallas, and I spent some time in Dallas. Had a lot of discussions with him. First of all, he never bothered to make a PhD. Nonetheless, he became a professor in Dallas. This was possible at this time. And at least in his first 10 years or so, he didn't bother to publish. So there are many papers on gravitational waves by Pirani, by Ehlers, by Kund, and so on. And you always have this remark, Ivor Robinson, quotation, Ivor Robinson, bracket, private communication, or unpublished. Yeah? So there were some notes by Robinson floating around, but in the beginning he never bothered to publish this properly. Then later he began with publishing. Unfortunately, he passed away last year, and he was very ill in his last years. And while the other one, Andrzej Trautmann, he's still with us. He's a Polish mathematical physicist who also did very important contributions to various aspects of gravitational waves. Okay, so what's the idea? The idea is, first of all, what's the goal? What do we want to describe? We want to describe vacuum solutions. So we are outside of the sources, and the sources should be bounded. Yeah, so the entire source, the entire region where the energy momentum tensor is different from zero should be within a sphere of finite radius. And then we would have outside of this sphere, we would have something which is expanding. So we would have, well, let's see, what did we have in the case of the plane waves? We had these rays. I denoted them, this vector field I denoted d by dv. Yeah? d by dv was a vector field, and the integral curves of these vector fields were parallel rays. Yeah? And they generated these plane surfaces, u equal constant. And in the cylindrical case, we had these surfaces rho plus Ct equals 0, or rho minus Ct equals 0. One was ingoing, one was outgoing. And again, these are light-like hypersurfaces ruled by light-like geodesics, by rays. So these are the vector fields d by d rho plus 1 over c d by dt, and d by d rho minus 1 over c d by dt. These are the light-like vector fields which generate these surfaces. And now we want to have something which neither generates planes nor cylinders, but something which is expanding, which is going outwards. So it's similar to a light cone. Yeah? A light cone is something which expands outwards. It's a light-like hypersurface which expands outwards, and the section at a certain time is a sphere. Topologically, at least, it's a sphere. And we want to have something similar of this now for this class of solution. So this would give gravitational waves of bounded sources, of bounded sources where the gravitational field then, or the gravitational radiation expands out to infinity. And what Robinson and Trautmann did was that they recalled how a very similar situation in electrodynamics is. In electrodynamics, actually, you can construct such families of light-like hypersurfaces which expand out to infinity. And you do this, for instance, when you consider the electromagnetic field produced by a moving point charge. So the analogy is the radiation in electrodynamics. So this is not gravitational radiation, it's electrodynamic radiation. From a moving point charge. And well, you usually do this on Minkowski spacetime. There are generalizations to curved spacetimes, but the standard form is that you do it on Minkowski spacetime. And on Minkowski spacetime, actually, you can solve this problem analytically. You can write down the solution for the electromagnetic field produced by a moving point charge, and the solution is known as the Leonard-Wiechert potential. Yeah? And how does it look like? Oops. So you have here the world line of your moving point charge. This is now a world line on Minkowski spacetime. And from each point of this world line, you have the future light cone issuing into the future. And the Leonard-Wiechert potential is the electromagnetic field which is produced by this moving point charge, and it is given, it can be written down analytically, really, by considering first the Coulomb field produced by a point charge which is at rest with a momentary velocity of the charge. So you construct on this light cone the Coulomb field, which falls off with 1 over r, the potential falls off with 1 over r, and then you add something which is sometimes called the Larmor term, which takes into account the acceleration of the world line. This produces a radiation field which falls off faster than the Coulomb field. And this, the combination of the two things, of the Coulomb field and of the radiation field, that's called the Leonard-Wiechert potential. And the essential thing is that these fields are constructed on these light cones. So for each point you construct the light cone, and then you write down this potential on the light cone. And this was the guiding idea for Robinson and Trautmann for constructing gravitational solutions with gravitational radiation. So the idea was, look for a space-time which is foliated into light-like hypersurfaces. And these light-like hypersurfaces should have this analogous properties to these light cones in Minkowski space. But now we are not on Minkowski space, we are in space-time where we have actually gravitational waves. And well, what are the properties? First of all, they are light-like hypersurfaces. That's the first thing. So I have a family of light-like hypersurfaces in which my space-time is foliated. And then the additional properties are, as you can prove, this family of hypersurfaces has the following property. Of course, it's generated by light-like geodesics. Yeah? Every light-like hypersurface is generated by light-like geodesics. So these are just the light-like geodesics issuing into the future from the various points of this world line. So this light-like geodesic congruence actually, in this case, turns out to be shear-free. Yeah, if you have a motion, you also do this in ordinary fluid mechanics, for instance. Whenever you have a motion, you decompose the gradient of the velocity into symmetric and antisymmetric part. And from the symmetric part, you extract the trace part, the pure trace. And what is left you call the shear. Yeah, this is a motion which, in one direction is expanding and in the other is contracting. And if you do this for this kind of light-like motion, you find that in this case, the shear is 0. So Robinson and Trautmann said we are looking for solutions where the shear is 0. But of course, the expansion, this is given by the trace of the gradient. The expansion should be non-zero because we want to have something which expands out to infinity. So the goal is find solutions to Einstein's vacuum field equation that admits a family of light-like hypersurfaces generated by light-like geodesics, whenever you have a family of light-like hypersurfaces, they are generated by light-like geodesics, and the properties these light-like geodesics should have is that they are shear-free. This was just by analogy to this case. So actually, from the physical assumptions, what you expect from gravitational waves, there would be no reason to require them necessarily to be shear-free. But it was just made as a simplifying assumption motivated by this analogy and expanding. Yeah, so the expansion should be non-zero and positive, shear-free and expanding. So that's the goal. And the question is, how does such a solution look like? And Robinson and Trautmann solved this problem completely. So they gave the general form of these metrics, and they also discussed a couple of examples. So, well, let's try to find out how the metric would look like in this case. So we have, by assumptions, we have this family of light-like hypersurfaces. So let's call of course I can label them by a certain scalar function. Let's call this sigma. So the surfaces, or hypersurfaces rather, sigma equal constants, these are these light-like hypersurfaces. And then I have the geodesics which generate them. Yeah, these geodesics, this is the gradient of, so let's call it K mu. So K mu, let me write it this way. K mu is just z mu nu d nu sigma. Yeah, it's a gradient of this function sigma. This vector field, because the hypersurfaces sigma equal constants are light-like, this is a light-like vector field, and the light-like vector field is perpendicular to itself. Yeah? So the gradient, I mentioned this already several times in this Lorentzian geometry, has for light-like, in the light-like case, different geometric properties from what you are used to from Euclidean or Riemannian geometry. There the gradient is always transverse to the surfaces. Here in this case, the gradient is tangent to the surfaces. yeah, because it's light-like. So this is what's often called, these integral curves of K-mu is what's often called the generators of these hypersurfaces. Yeah? So they rule these hypersurfaces. They generate them in a certain way. Okay, now we ask ourselves, or rather Robinson and Trautmann asked themselves, how could we parameterize such a spacetime, coordinatize such a spacetime in a convenient way? Obviously, sigma is a natural candidate for one of the coordinates. I would use sigma as one of the coordinates. What could be the other coordinates? Well, I could choose. Let me see if I can draw this in a way that you can recognize what I mean. So you can cut your family of hypersurfaces with another hypersurface, which is transverse. So then you get something of this sort. Let me see if I manage to. No, that's not how it is. This intersects here, so this way. Oops. It should be transverse, yeah? That's not a good picture. Let me do a new picture. Oops. Let me here just leave what we had before. These hypersurfaces sigma equal constant, and here these light-like geodesics by which this is ruled. K mu. And now I cut my family of hypersurfaces transverse. Yeah, I think that's better. Nonsense. This is visible. This is also visible. Okay, not very nice, but I hope you get the general idea. Yeah, so if I have one of these surfaces, then I can transport them with the flow of this vector field K mu. So I can transfer this with a vector field K mu. If I call one of these surfaces, if I label them with a number rho naught, say, then these other hypersurfaces would be labeled with other numbers of rho, where the flow of K mu maps these surfaces onto each other. So these surfaces then become surfaces rho equal constant. And the fact that they are transported with the flow of this vector field means that K mu d mu rho is equal to 1. Or what is the same thing, this vector field, which I denoted K mu, which is tangential to these hypersurfaces, just becomes one of the Gaussian basis vector fields, namely the vector field d by d rho. So we have now coordinates sigma and rho. So we have now coordinates sigma and rho. Two are missing, so I have rho and sigma. And by construction, I have K mu d mu is just d by d rho. Yeah, it's constructed in this way that the vector field K mu transforms the surfaces rho equal constant into each other. So what is still missing to make this a coordinate system is I have to introduce two coordinates on these intersections. Yeah? This is a three-dimensional hypersurface. This is a three-dimensional hypersurface. They intersect. If they intersect transversely, which by construction they do, they give the intersection is a two-dimensional hypersurface. Not hypersurface, a two-dimensional surface. So I need coordinates on these two-dimensional surfaces. And here I denote these coordinates xi and eta. Yeah. So on each of these two-dimensional surfaces, I introduce coordinates xi and eta. And because I already have these these coordinates sigma and rho, I can do this in the following way, that I parameterize it just on one of these two-dimensional surfaces, and then I transform them with a flow of rho and with a flow of d by d sigma, which goes in this direction now. This becomes d by d sigma. And then I get a coordinate system on the whole space-time. Yeah? So actually what we are planning to do is we want to have a situation where these hypersurfaces are something like expanding light cones. Then these intersections would be spheres. Yeah? So then you would use something like theta and phi for the coordinatization. But for the time being, it can be just any set of coordinates. So that's the way in which you would coordinatize a space-time which has this family of distinguished light-like hypersurfaces, sigma equal constant. And now you can write down the metric. So you have certain, by construction you have you have constructed the whole thing in a way that some of the metric coefficients are independent of some of the coordinates, because, for instance, by this condition, you just transport them with a flow of one of these coordinate vector fields. So if you use these assumptions, you get a particular form of the metric expressed in these coordinates. And let me write this down now. So this, until now, we have not used anything of the field equation, and we have not used anything about these congruents being shear-free or expanding or something like that. It is just the property that my space-time is ruled by or is foliated into a family of light-like hypersurfaces. So maybe I draw another picture where I indicate all four, or, well, I cannot indicate all four coordinate basis vector fields, but at least three of them I can indicate in one picture. Oops. Wo ist der? Ah, okay, danke. Ups. Das ist praktisch. Okay, let me see. So we have here, this is one of these hypersurfaces. Here is this two-dimensional section of this three-dimensional hypersurface. And then we have d by d rho in this direction. Yeah? D by d rho is a vector field which has the generators of these surfaces as integral curves. Transverse to this, tangential to the hypersurfaces rho equal constants, I have my d by d sigma. Yeah? So sigma labels the different hypersurfaces. So d by d sigma is transverse to these hypersurfaces. And then I have here tangential to this two-dimensional sections, I have d psi and d eta. Of course, in the picture it looks one-dimensional because I cannot produce a four-dimensional drawing. But you should keep in mind this is actually two-dimensional. And you might already imagine something like sigma being, having spherical sections. Yeah? So it's something like a light cone going out to infinity. That's the case we are interested in. Okay, and now we impose additional conditions. So So our vector field k mu d mu, which is the same as d by d rho in this coordinate system, is shear free. So what's the shear? If you consider the gradient of a covector field, you have to pull one index. Yeah, because I want to talk about this being symmetric or antisymmetric, so I have to have both indices in the same position. So I have a vector field, k mu, a light-like vector field in this case. I pull the index down, and then I consider this gradient. The antisymmetric part of this, this is what one calls the twist of the vector field. And the twist is automatically 0 in this case because my vector field is surface forming. Yeah? This is an identity. The twist is always the same. The condition of being twist-free is equivalent to being hypersurface orthogonal. Here it is. Yeah, so well, the usual convention is that one puts a factor 1/2 in front of this. So this is omega mu nu, this is 1/2, this expression. That's what one calls a twist, and this is in our case, this is 0. Then one defines the expansion. This is a scalar, theta, so it has no indices. It is just a trace of the derivative. So this is, well, actually, I should have, no, I should have been more careful. Wait a minute, I jumped ahead a little bit. So we have these 4 coordinates. And what I'm doing here, this decomposition of the vector field, is done in the 2 surface perpendicular to the direction in which the vector field propagates. So what I consider is only this 2-dimensional hypersurface. And let me use capital indices here. And this is only takes values 1 and 2. So it only refers to these 2 coordinates. So it lives in the space perpendicular to the direction in which the rays propagate. And for this reason, the trace is this here. Yeah, it's a 2-dimensional trace. And the rest is a shear. The rest of the symmetric part is a shear. So the shear usually denoted sigma AB. So this is a symmetric part, and the shear and the expansion subtracted. So it's 1/2, the symmetrized thing. And then the trace subtracted. I'm in a 2-dimensional space, so I have to write theta over 2 times the delta AB or GAB. Yeah, it's not necessarily delta AB. I haven't said that I have normalized these coordinates psi and eta. I could do it, of course, on one hypersurface, but it's not guaranteed that it is preserved. Yeah. So if I choose my coordinates orthonormal on one of these surfaces, then it may well be that by transporting this with the vector fields d by d rho and d by d sigma, the condition GAB equal delta AB is violated. So I just left an arbitrary GAB here. So, and the condition now that the shear vanishes means that this must be 0. So that's the additional condition. So as I said, for gravitational waves, there's not necessarily, one need not require the shear to vanish. You could also imagine these outgoing families of light-like hypersurfaces with shear. And actually they are considered. So in follow-up papers, people considered generalized Robinson-Trautmann spacetimes where the shear condition was dropped. But in the original condition, in the original paper, the authors assumed this. And then they developed the general form of the metric. This is actually a fairly long calculation. So I have typed it out here. So you have to look at all possible metric coefficients, and you have to check in which way you could simplify them, so which of them you can make to 0 by appropriate coordinate transformations, which are still allowed. And in the end of this rather long calculation, so general form of the metric, which I will now give you, a form of the metric is then the following. So you have these coordinates, psi, eta, rho, and sigma. So I give you the metric in these coordinates. So there's a function 1 over capital P squared. I tell you in a minute on which variables the functions depend. And a big bracket, d psi minus a d rho squared, d sigma, sorry, d sigma, plus d eta minus b d sigma squared, bracket closed, plus 2d rho d sigma minus c d sigma. Oh, c is not the speed of light, c is a coefficient, sorry. But it's a notation from the original paper. So I have 4 functions. You see, I have 4 functions. I have the p, the a, the b, and the c. And yeah, these functions depend on everything with the exception of let me see. At the moment, they depend on. Oops, I should have written this somewhere. So they definitely depend on psi and eta. And at the moment, I think they depend on all 4 of them. Yes, I think at the moment they depend on all 4 of them. This comes later, that we specify this dependence. Where P, A, B, C are functions of psi, eta, rho, and sigma. Okay, so you see the surfaces rho equal constants are light-like. Yeah, there's no term d rho squared. And the surfaces, no, wait a minute. Sorry, the vector, no, nonsense. The vector field d by d rho is light-like, yeah, because there's no term d rho squared. Yeah? If you transvect this with, or if this is a second rank tensor field, if you put the vector field d by d rho in both slots, then you see you get 0, because you don't have a d rho squared. So this tells you that the vector field d by d rho is light-like. Yeah? And these are the generators of our hypersurfaces. From this form, you cannot immediately read that the surfaces sigma equal constants are 0, are light-like. What you have to do is you have to invert the metric. And then you see that the G with the upper indices doesn't have a G sigma sigma. This tells you that the surfaces sigma equal constants are light-like. Well, it's not very difficult to invert this metric. And then you will actually see that the G upper sigma sigma is indeed 0. And well, for this form of the metric, you can then also calculate the shear of the vector field d by d rho, and you will find that it is 0. And this is a general form of a metric which satisfies these conditions. So this already requires some calculations in order to arrive at this step, and then the real hard work begins, because then you have to plug this into Einstein's field equation and to solve Einstein's field equation. So inserting into Einstein's field equation, vacuum field equation, and when evaluating Einstein's field equation, you use actually also the condition that the theta is different from 0. That this theta, because you divide by the theta at one point. Inserting into Einstein's field equation and assuming theta, actually we are interested in the case that theta is bigger than 0, yeah, really expanding. You can construct analogous families, of course, with theta smaller than 0, but you really have to assume that theta has no zeros. This goes into the derivation. Results in the following. So the matrix then can be simplified. So in particular, you see that you can kill the A and the B. Yeah? The field equation, the vacuum field equation, allows you to kill the A and the B, and it gives you differential equations for the remaining things, for the P and the C. And I write just down the result. As I said, it's a long calculation. So the matrix then becomes simpler. There are only two unknown functions involved. This is, here I have a capital P. I now have a lowercase p. Oops. Here we are. So this is rho squared over lowercase p squared. And now I have only the psi squared plus the eta squared. So as I said, with the help of the field equation, you kill the A and the B. And then you have what we had before, 2d rho d sigma, and the C, d sigma squared. And of course, you get differential equations for P and for C. And now the metric functions depend only on psi, eta, and sigma, where P and C are functions of psi, eta, and sigma. So they are independent of rho. So if you go from one hypersurface to the next with a flow of rho, then these functions are do not. Oh, the C does depend on rho. Sorry, P is independent on where P is a function of psi, eta, and sigma, and C is a function of all four, actually, rho and sigma. I will write down the C in a minute. So the equation we have actually to solve is an equation for P, and then the C is given algebraically. So now I write the differential equations. The differential equation, actually they have a rather funny structure. Einstein's field equation is a second order differential equation, right? So you expect second order differential equations for these coefficients. That's what you get. But if you differentiate one of these equations two more times, then you see that you can express the C in terms of the P, and you end up with a fourth order differential equation for the P. Yeah? So you can decouple the system by differentiating two more times, and then you end up with a fourth order differential equation for P. So with this technique, you actually have to solve a fourth order differential equation, which is called the Robinson-Trautmann equation. And I'll give it to you in a minute. So this is the differential equation for P. I should introduce this Laplace operator. It's a modified Laplace operator. I'll tell you in a minute what it is. So the Laplace operator squared, that's a fourth order differential operator, right? Plus 12 m of sigma, a function m which depends on sigma, d sigma ln p, minus 4 this function m of sigma differentiated, 0. C is then given in terms of P. C is 2 rho ln, d by d sigma, ln P plus del tilde ln P minus 2m of sigma over rho. This is a modified Laplace operator on the 2 space transverse to the rho and sigma surfaces. So it is a second derivative with respect to psi, plus the second derivative is eta, but it's modified by a prefactor, which is p squared. Yeah? So it's an operator that lives on these two-dimensional surfaces, which we assume to be spheres, actually. And it appears twice. So and an arbitrary function. It comes in as an integration constant, m of sigma. It is usually called the mass function. We will understand in a minute where this name comes from. So what you can do in order to construct such a solution to vacuum's field equation is the following. You choose a function m of sigma. Then you solve this differential equation. This is called the Robertson-Trautmann equation. So, of course, it has many solutions. Yeah, it's a partial differential equation, so it has a whole solution space. Again, it's a linear differential equation for L and P. Yeah? So again, the differential equation you actually have to solve is a linear differential equation. No, sorry. Oh, this is nonsense what I said, because I have this also in the operator. Sorry, this is nonsense. It's not a linear equation. It's not a linear equation. The P is also in the operator. This is a little bit, misleading. But it's common to introduce a symbol for this operator. So you should always keep in mind that the P is in this operator also. So it's not a linear differential equation. But nonetheless, it's a partial differential equation which has a certain solution space. So if you have chosen your function m of sigma, you can solve this differential equation. And if you have found a solution P, then this equation gives you C, just algebraically. You just have to calculate it. And then you plug it into the metric, and this gives you the solution. And so there are two ingredients which you have to choose, right? You have to choose this function m of sigma, and you have to choose one particular solution of this partial differential equation. And in this way, you can construct a large family of vacuum solutions. Some of them can be written down really explicitly. If you have analytic solutions to this partial differential equations, and all the other ones can be studied numerically by solving this differential equation numerically. And as I said, we are interested in particular in the case that these coordinates psi and eta parameterize the sphere. Yeah, so that these surfaces where the hypersurface sigma equal constants and the hypersurface rho equal constant intersect each other, where this is a sphere. Actually, the paper by Robinson and Trautmann had something of spherical gravitational waves in the title. That's a bit confusing, right? So if you read it as exactly spherically symmetric, then of course you would say something like that doesn't exist. But that's not what they mean. They just mean that the wavefronts are topologically spheres, yeah, but not that you have perfect spherical symmetry. Let's see, I'm not sure if I have the title somewhere written in my notes. I thought I had. Now I have mixed up the pages completely. Here we are. Here, some spherical gravitational waves in general relativity. That's the title of this paper. It's from 1962. So spherical gravitational waves, that sounds strange, right? But I explained what they actually mean. So it's waves which are going out from bounded sources, yeah? And then they distribute, if you are sufficiently far away, over spheres. Okay, of course there's one solution in this class which everybody knows. Which solution do you expect to be in this class? Vacuum field equation. Family of light-like hypersurfaces which are expanding outwards. Remember such a solution? Of course, Schwarzschild is in this solution. Of course, has nothing to do with gravitational waves, but it must be in this class of solutions. Do you have an idea in which coordinate system we will get Schwarzschild? The coordinates are adapted to a family of outgoing light-like rays. Yeah, it's the outgoing Eddington-Finkelstein coordinates. And let me just point out by which choice of M and by which solution P you get Schwarzschild. Well, the reason why this is called the mass function is that for the Schwarzschild case, m of sigma is just a constant mass. Yeah. So Schwarzschild is contained by choosing m of sigma m equal constant. It's a mass parameter in the Schwarzschild spacetime. So the Schwarzschild radius is just 2m. M is the thing with the dimension of a mass. So it is the mass in SI units multiplied with g, gravitational constant, divided by c squared. And the p, okay, then you have to solve this differential equation where this is a constant and this is 0. Then it's actually not too difficult to find a solution. And the solution is this. P is, in this case, it's independent of sigma. It is 1 plus 1 over 4 psi squared plus eta squared. Yeah. So if you plug this into this differential equation with m of sigma equal a constant, then you see that it is actually satisfied. And yeah, the psi and the eta, these are now coordinates on these two surfaces, transverse to the outgoing rays. So in the Schwarzschild case, these are of course the spheres, which we usually coordinatize by theta and phi. By choosing NP, where psi and eta, these Cartesian-like coordinates, look at the metric. Yeah? So they have a Cartesian-like property. So if you want to transform this into the usual angle coordinates, then you do the stereographic projection backwards. So psi and eta are coordinates in the plane. If you want to have coordinates on the sphere, you do a stereographic projection backwards, and this means the most convenient way of writing this is to combine them into a complex coordinate. Then you have 2 times the tangent of theta half e to the I phi, right? E to the I phi. Yeah. So if you take the real part of this, then you get the psi. It comes with cosine of phi, and the imaginary part gives you the eta in terms of sine of phi, and this is precisely the form for the stereographic projection. So then the metric, this metric, yeah, with this particular p and with psi and eta expressed in terms of the angular coordinates, then what you get is this. You get rho squared sine squared theta d phi squared plus d theta squared. It is this term here. It comes from this term here. You also have, let me see. It's precisely this term. It's precisely this term. Plus 2d rho d sigma minus 1 minus 2m, which is a constant in this case, d rho d sigma squared. And you see this is indeed the Eddington-Finkelstein representation of Schwarzschild. So this is Schwarzschild in outgoing Eddington-Finkelstein coordinates. Where rho is what one usually calls r, and the sigma is this Eddington-Finkelstein time coordinate. I think I usually denote it t hat. Yeah, so if you in my lecture notes of the GR course, this coordinate, which is now the sigma, is c times t hat in this notation I had used for the Eddington-Finkelstein coordinates. So, okay, Schwarzschild we knew before. Yeah, this is not what is a great achievement that we have rediscovered the Schwarzschild solution. And Schwarzschild has nothing to do with gravitational waves, of course. So there are these expanding families of rays, but they are not associated with outgoing radiation. Yeah, they are just associated with a static field, with a time-independent field. But if you choose an M which does depend on sigma, then you can construct solutions which actually describe outgoing gravitational waves. So the fact that M is then not a constant, this reflects the fact that your system loses mass in the form of gravitational energy. Yeah? So you would usually consider solutions where the M prime is negative, yeah? Where in the course of time the mass becomes smaller. So sigma is kind of a time coordinate. I still have this on the board. Look, here in this case, as a function which labels the light cone is just the proper time on this curve. Yeah? Each light cone is labeled by the time coordinate of its vertex. Time coordinate refers to proper time on this world line. And in this sense, the parameter which labels these hypersurfaces may be interpreted as a generalized time coordinate. So here's a sigma as this generalized time coordinate. And the fact that M depends on sigma means that that's the mass, which is a constant for Schwarzschild, that this now becomes time dependent. And if you want to have something which is radiating outward, you would consider solutions with M prime of sigma negative. And M itself, of course, positive. Yeah, you can also have solutions where M is negative, but this would not be considered physical. So the physically relevant solutions are the ones where this is positive and this here is negative. These are the physically relevant solutions. And they describe systems losing energy in terms of gravitational radiation. Okay, there are, I mentioned only Schwarzschild as a special case. Those of you who know the C metric, this metric of an accelerating black hole, this is also included in this form of the metric. So the C metric is a black hole which is accelerated linearly in a certain direction. So Gary Gibbons uses to explain this in the form put a rope to a black hole and pull, and what you get is a C metric. As a metric in the exterior of the black hole is a C metric. That's also included in this class, and several other known solutions. But in particular, the interesting ones are the ones which are not stationary. Also, the C metric is stationary. The ones which are actually radiating, which radiate gravitational energy into infinity. And as I said, there's a generalization where this condition of being shear free is dropped. So you then have a bigger class of gravitational wave families. Most of them cannot be studied really fully analytically, because it's not so easy to find a fully analytic solution for this partial differential equation. But as I said, you can study this for any function m of sigma you want to have. You can study this numerically, and this gives you a fairly realistic idea of how gravitational waves from bounded sources behave. So all of these solutions, by the way, have a singularity if you try to extend them as far as possible. But that should not come as a surprise. Okay, in the Schwarzschild case, of course, everybody knows there's a true curvature singularity at r equals 0. Also, the C metric has a singularity. It has even more singularities than the Schwarzschild spacetime. Also has a singularity on the axis. And all the other ones have somewhere in the interior region a singularity. And this, of course, just means that it cannot be a vacuum solution on the entire 3 space. Yeah? There must be the sources somewhere. And there where the sources are, the solution is not valid because it's a vacuum solution. Yeah? So I'm not at all bothered by the fact that if you extend them as far as possible, you always encounter a singularity. So it just means that you consider these solutions in a domain where they are not valid. You can only use them outside of the sources. So you have a spherical region in space, and outside of the spherical region, this is a very nice class of solution which describes radiation going outward. Oh, time is already out. Yeah, so these were the two classes of exact solutions I wanted to tell you about. So, and as I said, this is by far the most realistic of the three classes. The other ones are a bit over idealized, but on the other hand, this is also by far the most complicated of the three. Yeah. The Brinkmann waves are really simple. Yes, they have so many symmetries, you can calculate everything explicitly, very easily. Yeah, the Beck-Einstein-Rosen waves, they are reasonably difficult. The calculations are more involved, but you can handle them. And here this becomes really hard if you want to study them in detail, and maybe also construct light cones, to visualize light cones. With the help of Mathematica or something like that. So you have to solve this partial differential equations, which is a little bit involved. Yeah, this was what I wanted to say in this last round. Now we have 10 minutes or so for questions, if there are any questions. Yeah, that's a question.
Can this solution describe a radiating black hole or settling black hole?
You mean the process of collapse? So
well, yeah, let's say
yes.
the last stage of a collapse where the black hole radiates out all the asymmetries.
Yes, so the question was if this class of solution can describe the collapse, so the gravitational waves outside of a collapsing object. Yes, it can. Yes, it can. Of course, yeah, it's a particular class of collapse, of course, only, not every kind of collapse. So you still must have these families of which describe this outgoing radiation. Of course, they have a certain geometry. Yeah. So, for instance, they have the shear-free condition. I would expect this shear-free condition to be violated for many types of collapsing objects. And yeah, what else? Yeah, I think that's the only thing, right? Yes, okay, it should radiate in all directions. So you should have these wavefronts of spherical topology. But I think that's quite realistic for practically all kind of realistic collapse situations. Yeah, but the shear-free condition, this might be violated. Yeah.
And can we then asymptotically approach to the Schwarzschild solution, for instance, with this?
Asymptotically approach the Schwarzschild solution, in which you mean if it settles down to a Schwarzschild solution? Yes. Well, actually, yes, there are even solutions of this kind. Yes, there are solutions of this kind. So these Robinson-Trautmann solutions are discussed in fairly great detail in the book by Griffith and Podolsky. Yeah. So, of course, there's the original article, and then also there's a book by Jerry Griffith and Jiří Podolsky. I don't recall what the title of this book is. Something with exact solutions, or no? It's called Exact Spacetimes in General Relativity. It's a funny title, yeah. I would speak of exact solutions, not of exact spacetimes, but they chose the title Exact Spacetimes. In general relativity. Actually, all three classes of solutions which I discussed here are considered in this book. So the Brinkmann, the Beck-Einstein-Rosen, and the Robinson-Trautmann in general relativity. This is Cambridge UP. So maybe some of you know this, this encyclopedia-like book on exact solutions by, well, first edition was by Kramer, Stefani, Held, and McCallum. And then in the second edition also, who was it? Two more were involved. Honsolas, I think, and I think some more. Okay, anyway, so this is just a collection of all known, not all known, but many, many known solutions to Einstein's field equation. The physics of the solutions are not discussed in great detail. The book is fat enough, yeah. Just by collecting the solutions, it has become a fairly fat book. This book complements this solution book in a very useful way, because it looks in much closer detail at some families, some specific families of solutions which have physical relevance. Many exact solutions to Einstein's field equation have been found, which where we actually don't expect them to be realized in nature. Yeah, they are just mathematical solutions, but we would be very much surprised if we if we found something in nature which was described by them. In this book, they concentrate on solutions which might have some relevance to physics, and they discuss them, as I said, in great detail. So the Brinkmann solutions are discussed in this book, the Beck-Einstein-Rosen waves, and in particular the Robinson-Trautmann solutions. The chapter on Robinson-Trautmann is very good and very detailed. And they also discuss the situation that they match something with a decreasing m to a constant m solution. Yeah, so this would describe something like an object settling down as a Schwarzschild black hole, and then become static for late times. Okay, any more questions? And we call it a day. Okay, so see you sometime else.